Hi everyone, welcome to the General Maths Complete Course videos. In this video, we'll be looking at data types and distributions. So the lesson outcomes for this video are identifying and differentiating the different types of data, understanding how distributions of both categorical and numerical variables can be represented, displayed, and described, calculating measures of center and spread of data distributions, understanding the use of 68, 95, 99.7% rule to estimate percentages in the normal distribution, and to answer multiple choice and short answer questions about univariate data. So we'll get started with the different types of variables. So when we're describing data, there can be multiple variables that we might collect when we're collecting data. So those variables can either be categorical or numerical. Categorical variables usually represent qualitative data, such as names and categories, whereas numerical variables usually represent values, measurements, and mostly quantitative data. Categorical data can further be split into nominal and ordinal variables, where nominal variables do not have an associated order. An example of a nominal categorical variable could be, for example, someone's blood type. So that could be A, B, O, A plus, B plus, so on and so forth. So there is no specific order in the way in which someone's blood type can be arranged. However, variables can also be ordinal. And ordinal variables usually have an associated order. An example of an ordinal variable could be BMI index. For example, underweight, average, overweight, and morbidly obese. So in this case, we have a specific order in which the variables could potentially be arranged, starting from underweight all the way to morbidly obese. On the other hand, we have numerical variables which represent quantities, values, and measurements. And they can further be split into discrete and continuous variables. Discrete numerical variables usually represent quantities that we can count. An example could be the number of students in a classroom. So we can count the number of students in a classroom. However, continuous numerical variables are variables that we usually measure, or quantities that we usually measure. An example of this could be someone's height or weight. So these quantities we usually measure using a specific piece of equipment, and there could be a range of different possible answers or possible sort of values that the value could represent. Okay, so now that we know that the different types of variables that we can have, we'll now be looking at how we might be able to represent the data depending on what type of data set we have. So for univariate data sets with either categorical variables or numerical variables, we can represent them in many different ways. And depending on what type of data you have, there will be a more appropriate way in which you can graph that data. So for categorical variables, we can represent the data either in the form of data tables, two-way frequency tables, or segmented bar charts. And for numerical variables, we can either represent them as dot plots, stem plots, histograms, or logarithmic histograms. Okay, so now we'll take a little bit of a closer look at displaying categorical data. So the first way in which we can display categorical data is in the form of a frequency table. So a frequency table is basically a way of estimating or noting down the frequency in which a certain category appears within a sample population. So whenever you're collecting data, you might have your certain categories which you want to calculate information about. You can just calculate the frequency, and this would be in the form of a frequency table. Then we can further transform this frequency table into a percentage frequency table. And a percentage frequency table takes the frequencies and writes them down as a percentage of the total number of people that the data was collected from. A percentage frequency table is a lot more useful than a frequency table, as it's much more easier to estimate probabilities and also to just estimate, really core statistics that we're trying to get across from a data presentation point of view. We can also represent the data in the form of histogram, bar charts. A bar chart is basically a way of, again, representing the frequencies, but this way it's more of a graphical way. So as can be seen from this bar chart, we have the different categories along the x-axis, and we have the frequency along the y-axis. So for a bar chart, it's really important to make sure that your bars have the same distance between each other, whatever that distance may be, and that the thickness of each bar is also the same. And the height of the bar is representative of the frequency. So for example, for English, the bar reaches a height of 9. So therefore it means that 9 students have English as their favorite subject in this example. We can also represent the same data in the form of a percentage segmented bar chart. So percentage segmented bar chart just represents the percentage of all the students. So again, it's just another way of transforming a percentage frequency table, but this time it's in the form of a bar chart. So how high the bar reaches is indicative of the percentage of students that have the particular subject as their favorite subject. So for example, if we look at English, the bar reaches a height of about 7 or 8-ish%. So therefore 8% of students chose English as their favorite subject. So sometimes we can also have percentage segmented bar charts with values ranging from 0 to 100, and the thickness of each bar is representative of how much of a percentage that the students have picked as their favorite subject, such as for this example. But it can be applied to a whole range of scenarios. Okay, now we'll have a look at how we can display numerical data. So numerical data can be displayed very simply in the form of a dot plot. So in this case, we again have different subjects, but this time we are recording how many people or how many students have selected that subject. So it might appear really familiar to a percentage bar chart or a percentage segmented bar chart, but it's just a little bit different in terms of the representation. We can also have a stem and leaf plot. So a stem and leaf plot is basically where we are separating the data in a way such that we have a tens column, for example, 2, 2, 3, 3, 4, 4, and then we have all the digits that might represent it. So in this case, the key is 2 /2 gives us 2.2 degrees Celsius. So basically, this is just another way of representing numerical data. In this case, it's more useful for representing continuous numerical data, but can also be used to represent discrete numerical data. So just to quickly have a look at how we might read this. So if we have a look at just this number over here, so 3, what that represents is that we have a value in the data that is 3.3 degrees Celsius. So that's how we can read the stem and leaf plot. We can also represent numerical data in the form of a histogram. And this is a very common representation because we have a large range of values. So we have the x variable in the x-axis, and we have the frequency on the y-axis. So in this case, our x variable, the variable that we're recording, is beak length. So the way that the histogram works is it's sort of similar to a bar chart, but the only difference here is that we usually have ranges. So these values in this bar over here represent, all the values that were recorded that were between 21.5 and 22. Whereas this bar over here represents all the values that were between 22 and 22.5, and so on and so forth. So again, it's very similar to a bar chart, but this time the bars are connected and they represent a range as opposed to a single category or a single value. We can also represent the data in the form of a log base 10 histogram. So this is really useful for representing data where we have a really large range of values. So for example, values ranging from 0 all the way to 1,000,000. So if we were to represent that data in the form of a histogram, it would be really inconvenient because we would have a really large scale and it would be really hard to sort of get meaning from that large scale. So a log base 10 histogram uses the log scales where every number, so for example 1 is 10 to the power of 1. 2 is 10 to the power of 2. 3 is 10 to the power of 3. So let's have a look at what 3 represents in this log base 10 histogram. So what this 3 represents is that the log 10 of the area is equal to 3. So if we want to find what the actual area is, all we need to do is reverse this and we will get 10 to the power of 3, which is equal to 1,000. Next, we can also represent data in the form of a box and whisker plot. So a box and whisker plot is, we'll have a look at that in a little bit more detail, but it's a really good way of representing our descriptive statistics. But the main point that you should get from numerical data is that they all are a really good way of depicting the shape of the data and the way that the data is distributed. Okay, so now we'll look at the 5-number summary. So the 5-number summary is a set of 5 statistics that can help us quantitatively describe a numerical data set. So these 5 numbers can be calculated entirely on the CAS calculator. They can be calculated manually as well, but I wouldn't recommend calculating them manually because the calculator is much faster and gives you the 5 numbers that you need straight away. So always when you get a random sample of numerical data, so it only works for numerical data, when you get a list of data including numerical values, you're going to put this into the univariate data analysis function on your CAS and it will give you the 5-number summary. So the 5-number summary includes the minimum value, the Q1 or the quartile 1 value, the median, the quartile 3 value, and the maximum value. So we'll have a look at what these values actually represent in a box plot. So a box plot is the best way of representing this 5-number summary in a very graphical form, as opposed to just 5 random numbers listed sequentially. So the minimum is essentially just the lowest value in a data set. And the maximum is the highest value in a particular data set. So the Q1 represents the bottom 25% of the data. And the median represents the 50% of the data. So the median is at the 50% point of the data. So we have 50% of the data below the median and 50% of the data above the median. And then if we look at the Q3, that represents 75% of the data. So each quartile, you can almost say, represents 25% of data. So from the minimum to Q1, that's 25% of the data values. Q1 to median, that's also 25% of the data values. Median to Q3, that's 25% of the data values. And Q3 to the maximum is another 25% of the data values. So it's essentially splitting the graph to see where the data lies predominantly. So another thing that you might have noticed in this graph is the maximum. So the maximum here is represented as a dot as opposed to a line. And this is because the maximum is actually an outlier. So outliers in the data are basically values that don't lie within the general trend of the data and might be due to statistical errors or just values that don't lie within the general data. So maximum here is actually an outlier, and that's why it's represented as a dot as opposed to a line. And we'll have a look at how we can determine outliers. So when we're constructing box plots, a few key steps needs to be followed. So when we're constructing a data plot, the box plot, the first thing that we need to do is list the data in an ordinal manner. So starting from the lowest value all the way to the highest value. So in this case, we've just been given raw data, which is not ordered. So first step is we need to order that data, and that can be done easily on our CAS if it's being done by hand. Alternatively, as required for this course, you can do this entirely on your CAS. You can also sketch it on your CAS, but you can also calculate the 5-number summary, which is required to sketch the box plot on your CAS. So next, using your calculator, we will create the 5-number summary. So in this case, the minimum will be 18, the Q1 will be 36, the median will be 39, the Q3 will be 43, and the maximum will be 52. So next, we need to check for outliers by calculating the upper and lower fences. So the upper and lower fence formulas are listed in your formula sheet for General Maths, and they're given by Q1 minus 1.5 times the interquartile range to give us the lower fence, and Q3 plus 1.5 times by the interquartile range to give us the upper fence. So the interquartile range, which we'll have a look at in the next 2 slides, is just a measure of the spread of the data. And the way that IQR can be found is Q3 minus Q1. So the upper quartile minus the lower quartile. And in this case, when we find IQR, it gives us 7. So therefore, when we sub the numbers into the equation, so Q1 minus 1.5 times IQR, or 36 minus 1.5 times 7, we get 25.5. And then when we calculate the upper fence, we get Q3 plus 1.5 times IQR, which is equal to 43 plus 1.5 times 7, which is equal to 53.5. So the point of calculating the upper and lower fences is sort of like finding the boundaries of the data. And any values that are not situated within these boundaries are considered outliers. So in this data, any values that are below 25.5 will be considered an outlier. And any values above the upper fence of 53.5 will also be considered an outlier. And as we can see from the data here, we have a value of 18. So we have a value of 18. So this value is below the lower fence of 25.5. So that's why it will be represented as a dot on the data, on the box plot. So if we have more outliers or more values below or above the upper and lower fences, they will also be represented as dots. And the value that will be here as part of the box plot, it can be determined by the next highest value above the lower fence and the lowest value or the highest value below the lower fence. So essentially, if we ignore this outlier of 18, the next highest value is going to be 34, which is over here. So that is the next highest value. So therefore, that value will be represented as this minimum value over here. Although technically, the actual minimum value is still 18. But just when we're drawing the box plot, it will be represented over here as 34 as opposed to 18 because it is an outlier. And then we represent using a bigger line, the Q1, the median, the Q3, and the highest value, which is going to be 52. So there are no values above 52, so therefore that is the maximum. Okay. So now we'll be looking at the measures of center. So measure of center is just a way of measuring or describing the central point of a data or the central tendency of the data. So there are 3 ways in which we can do this. The first way is the mean. So the mean is essentially a value that you will get once you average all the data points and divide by the number of values that you have. And by doing this, what you're going to do is you're going to calculate the average of the data set, which is essentially the mean. However, since the average will include the outliers, your mean is going to be influenced by these outliers, and we call this a non-resistant statistic. So therefore, the mean is not a good measure of center if you have outliers in the value. So therefore, it will only be used for symmetrical distributions, as skewed distributions which contain outliers will affect the mean. Next, we have the median. So the median is the middle value of an ordered data set. So if you get a random data set and you ordered all the values and you found the value that was right in the middle, that would be the median. So the median is actually not influenced by the presence of outliers because if we have outliers, the median is still going to be the middle value. So the value of the outlier doesn't really impact what the median is going to be. So therefore, we term it a resistant statistic, a statistic that is resistant to the presence of outliers. And because of this, the median can actually be used as a great measure of center for all types of distributions, even when they are skewed. And lastly, we have the mode. So the mode is the most frequent value in a data set. And this is also a resistant statistic because it will not be impacted by outliers, unless the outlier is the mode. Okay, next we'll have a look at measures of spread. So looking at the measure of spread, we're looking at essentially how the data is distributed, how spread out it is. Is it very narrowly distributed, or is there a really big spread of the data? And there are three ways in which we can do this. Either through the range. So the range is just the difference between the smallest and the largest value in a data set. And the way that we calculate it is by subtracting the minimum value from the maximum value. And the range will actually not be influenced by outliers because it is a non-resistant statistic. So it actually will be influenced by outliers, and as a result, you cannot use the range to describe the spread of the data when there are outliers. And it can be influenced by outliers because, let's just say, the maximum and the minimum are both outliers. So obviously they're going to impact what the range is going to be. However, we can also describe the data using the interquartile range. So the interquartile range is a representation of the middle 50% of the data. So we've already actually looked at the formula to calculate the interquartile range, but it's essentially just going to be the Q3 or the upper quartile minus the lower quartile. And so this representing the middle 50% of the data, any values that are in the extremities will actually be ignored. So therefore it will not be influenced by outliers and is thus a resistant statistic. And lastly, we can describe the spread of the data using standard deviation. So the standard deviation is a measure of the amount of variation or dispersion of a set of data values. So essentially we're looking at how spread out the data values are from the mean. So it's using the mean as a reference to look at how the data values are spread out. The formula to calculate the standard deviation is quite complicated and is not required for the course. So therefore, whenever the calculation for standard deviation is required, you can use your calculator. Okay, so now we're going to be looking at the shapes and the distributions of numerical data sets. So there are three potential ways in which a numerical data set can look like when we have plotted it out in a graph. So we can either have negatively skewed data. So negatively skewed data is essentially where we have a tail towards the negative end of the data. And what I mean by the negative end is we have negative on this side and we have positive on this side. So negative being smaller values, positive being greater values. So for a negatively skewed data, we will have a skew or a tail towards the negative end of the data. And depending on if you're using a box plot or a histogram to represent the data, it will look like this or this. So just by looking at the graph, you should be able to determine what type of shape the graph sort of represents. However, if you don't have a graph, you can also use, or if it's not clear from the graph, you can also use descriptive statistics. So if you calculate the mean and median for the data distribution and the mean is less than the median, then we have a negatively skewed data. Alternatively, we can also have positively skewed data. So contrastingly to negatively skewed data, we have a tail now at the positive end of the data. And thus, it is why it is called positively skewed data. And in this case, the mean will actually be greater than the median. Okay, and then lastly, we can have approximately symmetrical data. So approximately symmetrical data is where we don't have any skews, and the graph is approximately symmetrical with a mode right in the middle. So in this case, the mean will actually be equal to the median because our data is symmetrical, so therefore the mean is not going to be influenced by any outliers, and the median is just the middle value anyway. So this is how you can describe the shape of the data. Okay, so now we're going to look at how we can actually describe numerical data. So on your SACs and exams, there will be a lot of questions where they will give you some data and they will ask you to describe the distribution of the data. So whenever we are describing numerical data, the first thing that we need to do is have a context sentence. So a context sentence essentially just provides context to the data. So what is the data describing? Is it the distribution of height? Is it the distribution of weight? Or is it the distribution of the number of kids in a family, for example? Next, we need to describe the shape or skew of the data. So describing whether the data is negatively skewed, positively skewed, or approximately symmetrical, and also talking about outliers. So if there are outliers in the data, then you need to mention them. But even if they aren't present, so if you have no outliers, you still need to say that there are no outliers present. You can't just leave this part of the paragraph blank. So you still need to talk or mention outliers somewhere. Next, we have measures of center. So you need to be describing your data using the measures of center, either the mean or the median. But depending on whether your graph is skewed or approximately symmetrical, you will use the median. So I will preferentially just use the median, regardless of what whether my data is approximately symmetrical or skewed. And for measures of spread, you can use the interquartile range, the range, or the standard deviation. Personally, you should always use the interquartile range because, again, it's a resistance statistic. So regardless of whether your data is skewed or if it is approximately symmetrical, the interquartile range will always be a good measure of spread. Okay, so now we'll look at a quick example. So here we have a sample where we have two parallel box plots, and we have to compare the distributions of these two data plots. So first step, you would just need to describe what the data represents. So the parallel box plots display the test scores between grade 1 and grade 2 students. Then we need to describe the shape of both of the data, both of the box plots. So the distribution of grade 2 scores on the test are negatively skewed, whilst the grade 1 score will be positively skewed. And then because we have no outliers, we still need to mention that there are no outliers. Then we can describe the measures of center. So I've chosen to describe the median here because, like I said, the median is a resistance statistic. So regardless of whether your data is skewed or approximately symmetrical, the median is always a good measure of center. So I've just described the median. I've compared it here. So I've said that the grade 2's median, and I've also quoted it. So quoting the values are really important in this case, as opposed to just saying, the one median is greater than the other. So the median score for grade 2's is higher, M equals 23. Then for grade 1's, median equals 9.5. And then I've also described the spread of the data using the interquartile range. So I've said that the IQR is smaller for grade 2's, IQR equals 10. Then for grade 1's, IQR equals 12. Okay, so that is how we can describe numerical data. Okay, so lastly, we're going to be looking at the concept of the normal distribution. So the normal distribution is a perfectly symmetrical data which exists a lot in nature, or natural distribution. So for example, height, weight, the size of an orange, for example, all of these are naturally distributed in the form of a normal distribution. So it just forms this distribution naturally. So basically, normal distribution has the mean equaling to the mode equaling to the median. So all three of these statistics will be the same. So frequency histograms and polygons, originally we don't really know whether the graph is normally distributed or not. So what we can do is represent it using a histogram. And when we do represent it using a histogram, overall we will see that the graph resembles something called a bell-shaped curve. So this is what the shape of the bell-shaped curve looks like. So it's sort of just an approximately symmetrical graph with sort of like skews at both ends. And it approaches zero on both sides. And since this graph is symmetrical and we have the median in the middle, 50% of the data values will lie on the left-hand side and 50% of them will lie on the right-hand side. So next, what we can use is the 68-95 99.7% rule. So basically, for a normal distribution, as shown in the previous slide, we can estimate what percentage of our data values will lie in certain, in certain regions. So let's just say we have a normal data that resembles a normal distribution, and we're trying to work out how much of our data will lie, one standard deviation either side of the mean. So for the normal distribution, we use the mean and the standard deviations in order to calculate the probabilities, or not the probabilities, but the percentages. So we have the mean in the middle, and then we have standard deviations on either side. So -1 standard deviation, +1 standard deviation. So let's just say the mean is, 0, for example. So I will quickly illustrate that. So let's say the mean is 0. So for the standard normal distribution, the mean is always going to be 0. And the standard deviation for the standard normal distribution is going to be 1. So we go 1 up, and we go 1 down, -1. And then we go -1 down as well. Again, so -2, and then -1 down again, -3. And then we can go up to 2 to 3. So this is really useful because now we know, how much of our data will lie between -1 and +1 standard deviations. And that's going to be approximately 68% of our data. So let's just say, we were looking at, just the height of individuals in the room. 68% of individuals in that room will have a height 1 standard deviation of the mean. So whatever the mean might be. 95% of those will have data values lying within 2 standard deviations of the mean, and 99% of the data will be lying within 3 standard deviations of the mean. So this is why it's termed the 68-95 99.7% rule. And lastly, we have Z-score calculations. So Z-score calculations are essentially when we're trying to compare data sets. So if we have 2 different normally distributed data sets with different means and different standard deviations, how can we possibly compare them? So let's just say you are a student who's doing English and also general maths. And let's just say you score 80% in general maths. And let's just say you score, 70% in English. So you want to actually compare your performance. How you went. So not just by what percentage you got, but in terms of the rest of the cohort. Because your English, SACs might just be a little bit harder as compared to general maths, which might be a little bit easier. So you want to compare yourself to the cohort. So in that case, what you might do is do something called a Z-score calculation. And what the Z-score calculation will do, it will give you a number within the range -3 to +3. So let's say you do it for English, where the mean was, 65% and the standard deviation was 1%. And if you do it for, if you do the z-score calculation, let's say you get +2, for example. So what that will tell you is that your value is actually 2 standard deviations above the mean. So you've actually done quite well compared to the rest of the cohort. And if you do that for general maths, let's just say the mean was 75, let's just say the mean was 90% and the standard deviation was 2%. And if you do it for general maths, let's say you get a z-score of -1, for example. So what that means is your performance is actually 1 standard deviation below the mean. So you've actually just done worse than the rest of the cohort. So this way it allows really good comparison between different pieces of data from different normal distributions by standardizing it to that standard normal distribution, which has a mean of 0 and a standard deviation of 1. Okay, so now let's move on to some questions. So first of all, we'll be looking at a multiple choice question. So here is a typical question that you're likely to get in the general maths exam. So we have a table from a sample of 7 drivers who entered a supermarket car park. The variables in the table are distance, sex, number of children, type of car, and postcode. And we're trying to determine the number of categorical variables in this data set. So let's actually have a look at all the variables and try to classify them according to what type of variable they are. So if we look at the distance is actually a quantity. So therefore, we will actually describe it as a numerical data value. So furthermore, distance can have a long range and is usually something that we measure. So therefore, it will be a numerical continuous variable. Next, if we look at sex, so it's either male or female. So in this case, we have 2 discrete categories and they don't have an associated order. So therefore, it will be a categorical nominal variable. Next, if we look at the number of children, so in this case, we're actually counting a value or a quantity. So therefore, it will actually be numerical, but in this case, it will be discrete since we are counting something. And remember, when we're counting something, it's always a discrete numerical variable. Next, the type of car. So in this case, the type of car is again a category, sedan, wagon, or other. So therefore, it will be a categorical variable. And in this case, although the data has actually been represented for the type of car in terms of 1, 2, and 3, the 1, 2, and 3 actually code for sedan, wagon, and other. So it's still a category. The numbers don't really represent anything. So therefore, it is still going to be a categorical variable. And also, since there's no associated order, because a sedan and a wagon cannot be ordered in a particular way, it will be a nominal variable. And lastly, the postcode. So the postcode is a little bit of a tricky one. So a lot of students will think that it is a numerical variable. However, the postcode is not really a quantity. It's just a sort of name, essentially, or a category given to the place where you live. So for a numerical variable, the numbers actually have to mean something. And for a postcode, 8148, for example, don't really mean anything. So therefore, it's again going to be a categorical variable. And since the postcodes cannot really be ordered in a particular way, it's going to be a categorical nominal variable. So overall, we have 1, 2 categorical variables. So therefore, our answer will be C. Okay, so here we have another multiple choice question. So in New Zealand, rivers flow either the Pacific Ocean or the Tasman Sea. So we have 2 different box plots and we're trying to determine the 5-number summary for the lengths of the Tasman rivers, which is closest to. So for the Tasman rivers, let's have a look at the minimum first. So the minimum is around here, which is approximately 32. So really having a look at the scale here. So each of the dots, each of the lines actually represent 10. So 10, so 20, 30, 40, 50, 60. So it's a little bit above 30, so therefore it will be 32. So immediately we can cross off D and E. Next, if we look at the median, it will, not the median, the Q1, it will be really close to 50, so about 48-ish. So we can't eliminate any further options. So let's have a look at the median. The median is between 60 and 70, so around 64-ish. So therefore, again, we cannot eliminate any of the answer options. And if we look at the Q3, that's between 70 and 80. So again, we cannot eliminate any of the answer options. So the maximum is actually the discriminator here. So remember the maximum, although technically this, we have, we usually think this is going to be the maximum, but it's actually this one, the maximum, the absolute maximum value in this data distribution is going to be the maximum. So therefore the answer here is going to be B. And lastly, we have a short answer question. So the mean and standard deviation of the two variables, population density and area for these 38 inner suburbs are shown in the table below. So one of these suburbs has a population density of 3,082 people per square kilometer, and we have to determine the z-score. So remember, the z-score formula is z-score is equal to x minus x mean over standard deviation. So in this case, the x value that we have is 3,082. Our mean, as determined from this table, is going to be 4,370. And our standard deviation is going to be 1,560. So therefore, our answer here will be negative 0.8. And then question I asks us to interpret what this value means. So if it's a negative value, what that means is that that value is going to be below the population mean, which is 4,370. And how many standard deviations below it is determined by the actual quantity. So it's negative 0.8. So therefore, what that means is that if we're looking at the normal distribution, it means that the 25%, Okay, so how many, so if we're just quickly interpreting what this negative 0.8 means, it just means that the population density of 3,082 people is 0.8 standard deviations below the population, mean population density. So in this case, it was not required to interpret what that meant, but it's really important to know how to interpret, because there have been questions in the exam which have asked students to interpret what the z-score means. And how many of these 38 suburbs are expected to have an area that is 2 standard deviations or more above the mean? So we're now looking at 2 standard deviations. So if we look at this normal distribution graph, we're looking at all the percentages that are 2 standard deviations. This is 2 standard deviations or more above the mean. So we can just add up the probabilities. So we have 2.35% and 0.15%. So whenever you're given a question like this, you should have a normal distribution graph in your summary book. And just using that, you should have these probabilities already written down. So depending on what type of probability you're calculating, you can just use the percentages that are written down. So it will be 2.35 plus 0.15, which is 2.5% of the data, which will lie 2 standard deviations or more above the mean. Okay, so that was it for today's lesson. We'll just do a quick review of what we have covered. So we've covered the different types of data and their distributions. We've looked at the graphical representations of data, both numerical and categorical data. We've looked at how we can describe data distributions in terms of center and spread. And we've looked at the normal distribution and the 68, 95, 99.7% rule. And we've also looked at some multiple choice questions and strategies. Thank you everyone for watching today this video, and I hope it has been helpful in learning about the different types of data and their distributions.